To a topologist, a coffee cup and the donuts are the same. Perhaps you have heard this before, and that's because a coffee cup and the donuts both have only one hole, and they both take on one shape through continuous deformation. Data can also have a shape: facial scans, image analysis, structural classification, and so on. And topological data analysis is actually the tool to help us understand the nature of a data shapes.
Hi, I'm Canon.
And I'm Laila, and today we are talking to you about how to use topological data analysis and persistent homology to predict properties in crystals.
Topological data analysis, which is TDA, is a topology-based approach to data research. Donuts and coffee cups are topologically the same. So what is not? A football. This is because, topologically speaking, an object cannot change the number of holes through continuous deformation. The holes in the donuts cannot disappear into a football. TDA, on the other hand, involves inputting data into a computer to form a point cloud map, expanding our data, connecting the points into lines, turning them to surface, and observing what's the shape the data takes on when expanded to different scales, and also how many holes there are.
Now that we have this new concept of topology in our minds, I would like to correlate it with chemistry and crystals. When we are working with crystals, we normally use different systems to categorize them. These systems are based on the symmetry and geometry of unit cells, the most basic repetitive structure in a crystal. With these classifications, we can get general information about the arrangement of the atoms in a crystalline network and use it to predict physical and chemical properties. Let's take the example of diamonds and graphite. Both are different crystalline structures of the same element, carbon. But despite being made of the same thing, one is known because its hardness and the other because how fragile it is. Understanding how crystalline structures determine the properties of a material is fundamental for research. However, the amount of relevant information that we can get from these models is limited. Here is where topological data analysis enters. By using topology, we can reach more fundamental features of crystalline structures, such as the presence of holes, voids, and loops. With these new informations, we are capable of improving our predictions and even predict more properties, as I'm going to explain later.
Although topological data analysis sounds abstract, well, in fact, it's a bit abstract. However, it can be done in just a few steps. First, we have to have a set of data and input it into the computer. In our case, which can be the coordinates of the crystal atoms, extracting them into a point cloud plot. This step is called geometrical realization. And the second part is the most important one, where we have to extract their topological features from the geometrical ones. The dominant approach is called continuous homotopy. Let's say now we have a set of data, and we define a scale or a threshold to be applied to each data point as a circle. The radius of this circle is uniform for all data, and the size of the radius can change over time. When the two circles have started to intersect, we connect to the data point to form a two-dimensional line segment. As this threshold continues to increase, higher dimensional complexes can be constructed. But wait, what is a complex? Simply put, a simplical complex is formed by several simplexes, and the simplex is the simplest unit for constructing the shape of a piece of data. In 0 dimensions, it's a point. In 1 dimension, it's a line segment formed by 2 points. And 2 dimensions is a triangle formed by 3 points. And 3 dimensions is a tetrahedron formed by 4 points, which in turn can be used to construct larger shapes and structures. We can see that as the radius changes, holes are formed, some of which are there for a long time, and some of which disappear quickly. In TDA, the main analysis is the existence and demise of holes. In fact, in the real life, we have to face a huge amount of data. We will hardly count number of holes one by one. And why not just leave it to the machine to do it? We can then transform topological spaces into algebra objects by using algebraic topology to simplify calculations and comparisons, as well as to combine with machine learning. This formula, HP, which is homology group in n dimensions, equals to the kernel in n dimensions divided by image in n plus 1 dimensions, can help us calculate the number of real holes. And if you have already studied the linear algebra, you are probably not unfamiliar with kernel and image. The meaning of this formula is whether the closed chain or kernel in n dimensions is bounded in higher dimensions. This formula can also be calculated using linear algebra. This formula can also be calculated using linear algebra. I know it's very abstract, but if you want to have more detailed explanation, you can come to our website for more information. There, we explain in detail what the formula means and how we calculate by using linear algebra, and also what is a real hole.
Now that my partner Canon has gone deeper on the basics of topological data analysis and persistent homology, it is time to go back to crystals. Once that we have computed the persistent homology, we can see that different barcodes were generated, specifically one per dimension. The length of the bars define the relevance of the features that they describe. Longer bars means more relevant features. But what are those features? Well, it depends on the dimension that we are analyzing. For H0, bars indicate clusters of atoms forming the structure's connectivity, giving a general description of atomic bonds. H1 normally corresponds to repeating cycles or port-like features in frameworks. These are holes previously mentioned that we previously mentioned, and are the ones that have some of the most interesting properties. Finally, H2 represents the presence of larger cavities and channels inside the structure. And how can we use this information? Well, as I mentioned before, it can improve our predictions. One example is the case of enthalpy of formation, a property that describes the amount of energy that requires to bind two substances to form a crystal. For the prediction of this property, it is a standard practice the use of density functional theory calculations. But recent investigations have proved that using topological data analysis can improve the accuracy of those predictions, passing from an average accuracy of 68% to an 85%. And this is not the only case in which we can use topology. One of the most intuitive applications is the tracking of points for doping. In crystallography, the doping consists of the addition of atoms to a crystalline structure in the free spaces, this with the purpose of modifying its properties. Topological data analysis provides just the ideal information to predict which kinds of dopings are possible in determined crystals. Just to finish, now I want to tell you that this is a remake of a previous video that we made. This new video is made based on the different feedback that you, our partners, provide us. In this new video, we have reduced the definitions of TDA related jargons and increased the examples and pictures, which hopefully can help viewers to understand. In addition to this, we have omitted the detailed explanation of formulas because for us, there is nothing better than a vivid example to help understand the nature of TDA as a tool and how to apply it. Also, there are a lot of details missing. We hope that our new additions can help viewers to understand this data analysis tool more quickly and raise their interest.